So in this lab, we're going to look at something called standing waves. So the idea is this: if I have a source of vibrations, so in this case a tuning fork, and I hold it over a cavity, there is some special length where this, this frequency will somehow fit into the cavity and it'll get really loud. It's how musical instruments work. So if you listen, you can hear right at that length, it gets really loud. So we say that the length of this air column, because there's air in this pipe, the length of that air column is the length of the cavity that causes this frequency to resonate, okay? So what I'm going to do is just go through a bunch of tuning forks here. You've already found the frequency of each one, and then what you're going to do is record the length of the cavity that causes it to resonate. So I will smack the tuning fork. I'll move this up and down till we get a really strong resonance. And so this tuning fork is G4, all right? So for G4, we can now measure the length of the air column. So the air column starts at the water level and goes up to the top of the pipe. So, whoops, I gotta turn this over. We gotta start at 0. So we'll start right here at 0, and you can measure the length of the air column right there, the top of the white pipe. That's the length of the air column that caused G4 to resonate, okay? All right, so we've got G4. We'll do a couple others, they'll go a little faster. The next one is F4. So this is F4. So right there, F4 resonated. And we shall measure the length of that air column. So there you go. You'll have to zoom in maybe and read it. Make sure you're in high-res mode on the video. So you can see the length of the air column that caused F4 to resonate. Okay, that was F4. Now let's go on. This one's a little hard to hear. This is C4. It's a little lower frequency. There it is right there. So let me hold that. So that was C4, and the length of the air column that caused C4 to resonate, you can measure. There you go. So you can read that off the meter stick. Okay? And of course, we're going to convert all these to meters right there. Okay? So that was C4. Okay, so now let's do A5. Right there is A5. The length of that air column caused A5 to resonate. So I will hold this at the water level, and you can read the length of the cavity that caused A5 to resonate. Okay. All right, next we have, this is E4. E is an elephant, E4. Looks like that length right there caused E4 to resonate. So I'll hold the meter stick up here, and you can, gotta move my hand out of the way. Here's E4, right there. Okay, that was E4. Okay, the next one is B5. Right there is B5. So I'll hold this on the water level, and you can read the length of the pipe that caused B5 to resonate. Okay, that was B5. Now we're down to D4. D as in dog. D4. Looks like it's right about there. So this was the cavity that caused D4 to get loud. We say resonate. And there you go. You can measure D4, the length of the cavity. So just measure, read at the top of the meter stick there. Okay, that was D4. And our last one is back to C5. So this is C5. Looks like it's right there, C5. So let me hold the meter stick up, and you can make your measurement for C5. There you go. Okay, so what you are going to do is you're going to make a plot showing how the length of the resonating cavity depends on the wavelength of the wave. So for each of these tuning forks, you know the frequency, you know the speed of sound, you can find the wavelength. And so you'll find the wavelength, and you'll use the length you measured for the resonating cavity, and you'll plot the data and see if you can find a pattern or a mathematical model. Okay?